In your previous science courses, you probably encountered the notion of density, especially in chemistry, in the context of mass density. How much mass of a substance is there spread out over some region of space? How much mass per volume? In SI, density would be measured in kilograms per cubic meter. If you think about a cubic meter is going to be a lot of stuff. 1 cubic meter of water is going to be a lot of water because that's 1 by 1 by 1 meter. I expect 1 cubic of meter to be many kilograms. It's actually 1,000 kilograms. If you think about the example of the 2 liter bottle of lead compared to the 2 liter bottle of water, in both of these cases, the amount of space that we occupy, the volume, is going to be the same. We have 2 liters and 2 liters of stuff in our bottle. However, lead is more massive than water. One lead atom is more massive than one water molecule. And because the lead is more massive, 2 liters of lead is going to be more massive than 2 liters of water. We could say lead is going to be more dense than water, and this is why lead sinks in water. On the other hand, if we were to compare a teaspoon of lead to a 2 liter bottle of lead, in this case, we expect the densities of the teaspoon of lead to be the same as the density as a 2 liter bottle of lead, because we are talking about the same substance in this scenario. In this case, what's going on is you have more mass in the 2 liter bottle of lead, but you also have more volume in the 2 liter bottle of lead. So even though the substances have the same density, the teaspoon has less mass, but it also occupies a smaller volume. So the density is still going to be the same if you compare a teaspoon of lead to a 2 liter bottle of lead. So very often, density is thought of as mass over volume, but we could generalize this idea. If I think of density as a quantity of interest divided by some geometric term, if I'm thinking mass density, the quantity of interest would be the mass, how many kilograms of my substance do I have, and the geometric term would be how much volume does that substance occupy, how many cubic meters does it fill. But I don't need to think of density as mass over volume. If I want to, I could think of density as, for example, how many sheep per square kilometer are in New Zealand. In this case, I would say the quantity of interest that I'm interested in is the number of sheep, and the geometric term is going to be how many square kilometers are the sheep spread out over. In this case, I'm using the phrase geometric term instead of volume because I'm talking about a 2D geometric term. I could talk about number of sheep per square kilometer. If you think of a lot of people standing in a long line, I could ask how many people are in each meter of that line on average. That would be like a linear density. Here I'm talking about an area density, and up here in this 2 liter bottle of lead, I'm talking more of like how much mass is spread out over a 3D region of space. So the dimensionality of the region of space that we talk about when we talk about density does not necessarily need to be in 3D space, although very often it will be. As an example of a density problem, radio is fundamentally a color of light, no different from green or blue or red or whatever else, except based on the biology of our eyes, we can't detect the color of light that is radio. So as a thought experiment, let's assume that the Earth has been transmitting radio waves for roughly 100 years. That means that our news, our nature documentaries, our pop culture references are traveling outward into the universe at the speed of light. It's actually been a little longer than 100 years, but we'll use 100 years just to keep our math simple. Let's make a very generous assumption that near any sun-like star in our galaxy, there's going to be a 5% probability of aliens having a civilization there that are able to pick up our broadcasts. So given that we have been transmitting radio waves outward, traveling away from us at the speed of light for 100 years, and given that there's a 5% probability of aliens around a sun-like star being able to pick up our broadcasts, estimate the number of alien civilizations that have picked up and began overly repeating our pop culture catchphrases. And we'll make the assumption that there are roughly 1.4 times 10 to the negative 4 sun-like stars per cubic light year in our galaxy. So after this video concludes, I will demonstrate this example problem along with some others. And if you're wondering, if you say we have been broadcasting in radio for 100 years, that means we are at the center of a 200 light year diameter sphere in our galaxy where aliens potentially could have picked up our radio signals because we're broadcasting in every direction, 100 light years that way, 100 light years the other way. That would be 200 light years across. So the sphere at which our radio waves broadcast would be about that big compared to the rest of our galaxy. Now, there are other problems with this, such as radio waves will get weaker and weaker as they spread out. Aliens need to be actively listening for it, and they will need a very dedicated telescope to be listening if they want to watch Bugs Bunny or whatever. But in principle, this can happen. Now, the concept of dimensional analysis is if you put a cat on a scale, you do not expect to read the mass of the cat in seconds. You put something on a scale, you want to measure the mass, you expect mass to be in kilograms. Similarly, if you measure the radius of the Earth, you want something that's measured with a length, not with a mass. So you would measure in meters instead of kilograms. Whenever you have an equation, the units on the left side of the equation should be the same as the units on the right side of the equation. So if I think of speed as distance traveled over time of travel, well, speed is going to be distance over time. Now, what do I measure distance in? I could measure distance in meters, or I could measure it in miles if I don't want to work in SI. I could measure time in seconds or hours. It's okay to do either as long as you're consistent. So however I measure speed, I could measure speed as miles over hour. And we do know from everyday experience, speed is measured in miles per hour. Now, whenever I add or subtract quantities, I need those quantities to have the same units. So if you imagine that I had plus some other terms out here, not a simple equation like this, if I have plus or minus signs, whatever this term is in, the term that I'm adding it to must be in the same units. If I multiply or divide quantities, the quantities do not need to be in the same units. I am allowed to divide one type of quantity by a different type of quantity. There's no rule saying I can't do that. Also, if I have a term inside a trig function, like I have sine of some quantities together, or a term inside a logarithm, or upstairs in an exponent, whatever is inside the trig function or upstairs in the exponent must always be just a number. It should have no units. So if you have something that is measured in meters, check around, make sure you're not accidentally forgetting to include something that has units that would cancel out the meters. Also, I want to add, don't really use this equation that I wrote here for actually solving any calculation. I just wrote this equation here because it's very short and simple and something we are all used to in everyday life. This equation does apply if you are moving at constant speed, which is a fairly narrow range of cases that we'll consider. There's a more general equation that I'll introduce in chapter 2. If you actually are solving a problem, you need to be allowing for the possibility that speed could be changing. The next idea I'm going to talk about is the concept of the coordinate system. Very often, what you will need to do is you'll need to fix the position of something relative to some agreed upon reference. When you fix a reference, you're essentially just defining a coordinate system. Now, coordinate systems are often referred to as X and Y, Cartesian coordinate systems, but I want to introduce the concept of the coordinate system in this way. Essentially, what we're doing is we're quantifying positions. And a example of a coordinate system that you have seen probably since kindergarten is the number line. So don't worry about X and Y Cartesian coordinate system. Think about the number line first and think about what is the number line. So you probably saw something like this before when you were introduced to a number line. You hear 0 and you have 1 and 2 and 3 and 4. And then when you went on a little bit in primary school, they could extend the number line backwards to negative numbers. So if I say I am right here, I am 4 units away from 0. The number line is an example of a coordinate system. If you could deal with one number line, you could deal with 2 number lines. So let's just take 2 number lines. We will set them to be orthogonal to each other, or we will set them to be perpendicular to each other. I'm going to call one number line X, and I will have that number line be horizontal. I will call my second number line Y, and I will have that number line be vertical to each other. By convention, we are setting these number lines to intersect at 0 on each number line. This is just a convention that makes our life simpler. There is no fundamental reason why we must do it this way, but we definitely make our lives easier by doing it this way. So X tells me where am I in relation to the X number line, and Y tells me where I am in relation to the Y number line. And that's all I'm doing. So let's say I don't want to be right here. What if I want to be down here? Well, my X position is the same down here. My X position is the same here. My X position is the same here. My Y position is changing, but everywhere along this line where I'm drawing my mouse, the X position never changes. And similarly, if I'm over here at X equals 3, Y equals 5, if I move to the left or to the right, my X position is changing now, but my Y position on the Y number line never changes. So X and Y are really just 2 number lines that are perpendicular to each other. We did not really ignore when I say how far to the right and how far up you are. I did not ignore left and down. Left is just negative right. Down is really just negative up. So I could think of this position as -1, which is the same thing as saying moving to the left. So to conclude this chapter, we're going to demonstrate several example problems on the board before we begin with the physics of chapter 2. I would say whenever you're encountering a problem, first of all, draw and label a picture of what you're trying to do. If you don't need your picture, that's fine, but having a picture drawn in front of you is very useful to help your brain think of what's going on, and it helps you see when it's right in front of you what is important versus what might be less important of a detail. Also, I want you to write out every step of the problem until you become super duper comfortable. Don't skip steps. Don't try to do everything at once. Some problems will have many steps. Leave enough space in anticipation that you will need to use many lines of work to get to the final result of your problem. Even if it's just a simple calculation like 2 times 3 plus 5. Do the 2 times 3 first to give you 6, then add 5 to give you 11. Have that be 2 lines of work. It just makes life go simpler. And don't try to do 5 things at once. When in life in general, whenever you're learning a new skill, it is normal for things to go slowly. It is normal to be unsure. So don't try to see everything at once. Just go with the system of what you're shown, set up the problem, solve the math, and just don't anticipate what's going to happen. Just see where it leads you. I'm sure you guys will do great in this course. I am here to help you. I want to see you succeed. Reach out to me if you have any questions. I will demonstrate example problems on the board. And to conclude, you guys will do great. Don't worry, relax. We are in this together. And if you have any question at all, please reach out to me. You'll be fine.